Okay. So this is Srikanth Yadav, working as Assistant Professor, Department of IT, VFSTR Dmt U2 University. So in the data mining lecture series, in the previous session we completed two important operations of data pre-processing, such as data cleaning and data integration. Now today in this session we are going to discuss about data reduction. What is the use of data reduction, how the data reduction is going to be applied in data pre-processing activity, and why we have to go for data reduction. We will see with suitable examples. Let's enter into the session. Now here data reduction is going to be applied when we are dealing with very large amount of data. In real-time applications, we are generating very vast and huge amount of data. When the data size is enormous rate or enormous size, there is a chance of having very high complexity in the form of dimensions. That means when the data set is having more number of dimensions, when we are using more number of dimensions, those more number of dimensions will lead to the complex activities while performing data analytical operations. So in order to reduce irrelevant and keep only the most or best relevant attributes, so that we can achieve the same results or same accuracy by reducing number of dimensions. Now how can we reduce those irrelevant dimensions, and what are the techniques which are available here? So here data reduction obtain a reduced representation of the data set. That means here we are going to apply some data reduction techniques. That means it is compared to smaller in volume, but it will produce the same results. Let us take one generalized small example. Let us take we are having a data set. In this data set we are having some 100 to more number of attributes. Let us say we are having 150 dimensions here. When we are having 150 dimensions, among these dimensions, if possible, try to reduce some of the irrelevant or unwanted dimensions. Let us assume here we are trying to reduce this 150 count to some 30. That means out of 150, we are trying to retrieve the best 30 attributes so that we can get the same result. Here we are not compromising at the result. Here we want to produce same result with reduced format of data set. Here we are not deleting any data set. Here we are not deleting any value. Here we are reducing the dimensions and we are taking only the reduced format of dimensions for obtaining analytical results. Now how can we apply this reduction, that we will see now. Now why we want to go for a data reduction? This is a fundamental question. Why data reduction is required? A database or data warehouse may store large amount of data in the form of terabytes or petabytes of data. When we are storing terabytes and petabytes of data, we may encounter some complex data analysis which may take very long time to run the complete data set. When the data size in terabytes and petabytes, this much amount of enormous data will lead to consume more time either to process or to analyze or to complete all data mining related activities. So in this aspect, to increase the efficiency rate and to decrease this processing time, we are going to use data reduction as a part of data pre-processing activity. Now here we will see what are the commonly used data reduction strategies. So here the commonly used data reduction strategies, here we are trying to remove unimportant attributes. This is the fundamental objective of data reduction. We want to reduce unimportant attributes, or you can say we want to remove unimportant attributes. Whatever the technique we are going to apply in the form of data reduction, this is the ultimate objective. Identify the unimportant attributes and remove. That means what we are doing reversely, we are keeping the most important attributes in the data set. Now to obtain this, the proposed objective, there are commonly and globally used approaches are there, using wavelet transforms or by applying principal component analysis or by using feature subset selection or feature creation. These are the commonly used approaches. We'll see one by one in detail. Now, in addition to those, we can also apply the numerosity reduction. The previous approach is dimensionality reduction. Now, under dimensionality reduction, there is one more operation that is called numerosity reduction. That means it can also be called as a data reduction technique. Now, under numerosity reduction, there is a possibility to apply regression operations to identify the linearity, or you can say dependency of each and every attribute on other attributes, or by applying or creating histograms, or by making clusters. That means while making clusters, we can see the outliers. When we outliers have been identified, those outliers we can treat it as unimportant attributes, or we can go for a sampling approach. That means selection of data randomly and selection of required data depends on the various sampling techniques. And we can also go for data cube aggregation. That means on multi-dimensional data model, we are going to apply data cube related aggregation operations. So these are the commonly used numerosity reduction, data reduction techniques. And also we can go for data compression. That means the voluminous of the data is going to be compressed by applying various data compression techniques. So the details of each and every technique we'll see now. Now first we'll go for what is a dimensionality reduction. That means under data reduction, what is a dimensionality reduction? If we are not going for dimensionality reduction, what is the problem will arise? The first and problem or foremost problem is curse of dimensionality. That means when we are having more number of dimensions on any complex data set, that dimensionality count may leads to curse to the entire data set. That means when we are having more number of dimensions, these dimensions will lead to the complexity of the data mining operation. That means it will become more complex to apply data mining operations in order to retrieve relevant results. When dimensionality increases, the data becomes more sparse in nature. So to reduce that sparsity or sparse nature of the data, we can go for data dimensionality reduction. And one more reason why you should go for dimensional reduction, that is density and distance between points. Here points means attributes. So when we want to remove unimportant attributes, we can't do it randomly. That means we can't pick an attribute randomly and we can't delete it. Here we have to compare the distance between each and every attribute by applying some standard similarity measuring techniques. Based on results of those measurable attributes or measurable techniques, we can go for a decision called dimensionality reduction. Now here we want to find out the density and distance between the points. Those points we will call it as attributes here, which is critical to clustering. That means when we want to find out a distance between points or attributes where attribute count is in larger scale, the calculation of the distance among all those attributes will also become a complex activity. Anyhow, we have to proceed with that because that is one of the best option to identify the important attributes. Now, using this approach, we can analyze what are the outliers which are there in the data set, and after that we can have a meaningful data set. When we are having more elements, what will happen? We can't find the best meaningful value here. So here we are requesting or we are applying reduction of dimensions. Now the possible combinations of subspaces will grow exponentially. That means when we are not removing dimensions or more number of dimensions we want to keep in the data set, that can leads to the exponential growth of the data when new data is arriving into the data set. And the next one, under dimensionality reduction, what we are expecting, avoid the curse of dimensionality. Reduce unimportant dimensions, and that can avoid the curse of dimensionality. And it will also help us to eliminate irrelevant features, and after eliminating those irrelevant features, we can make a noise-free data set. So here, using dimensionality reduction, we are trying to eliminate the irrelevant attributes or the features. So that can give a noise-free data set. And one more advantage is here we can reduce the time of processing or computation required in the data mining. That means after reducing the unwanted attributes, we can achieve lesser processing time that going to be used in data mining analytical operations. And one more advantage is while producing the results to the end user, we can go for a visualization. That means we can produce better visualized results with less attributes. And here, under dimensionality reduction, as we discussed earlier, we can apply these techniques. We can go for wavelet transform, principal component analysis, and supervised techniques are nonlinear approaches. Let's see how the wavelet transform and Fourier transforms are going to be applied. Here, the Fourier transformation and wavelet transformations have been displayed in the form of a sinusoidal waves here. Now in these sinusoidal waves, if we observe carefully, here we took two sine waves and their representation, and here two sine waves along with some noisy content here. Now if you look at carefully here, in the second graph, the noise has been dominated in the original information. Let's look at it here. In the original two sine wave forms, here we took some time in form of milliseconds, in the seconds, 0 to 1 second. If you look at carefully, two sine waves have been represented in two unique colors. Here, first sine wave has been represented using some green color. Second sine wave has been represented using a blue color. When we are trying to generate two sine waves together using a Fourier transformation or wavelet transformation, when a noise has been added in the data along with, if we look at carefully, it is very hard to find out where a green color signal in this. The complete noise has been dominated with the second sine wave. That means it looks like same. If you look at the blue color and the height of each and every signal, it indicates that it looks like a original data. But actually it is not a data, it is a noisy. Now it looked like a very complex activity. How can we eliminate this entire noise from the data set? So to avoid such thing, we can go for dimensionality reduction. So when we are having complex activity or complex attributes in nature, we can eliminate. Now here, if you look at carefully, the noise is going to be eliminated by applying some techniques. Here we can observe the frequency of the sine wave which has been used as an initial data set here. Here you can see there is less noise, or you can say zero noise has been created. So using wavelet transforms, we can go for dimensionality reduction. Now if you look at carefully in the given image, here the distorted image is going to be recovered using some image retrieval techniques, or you can say using some MATLAB applications. Here what they are using, they are decomposing a signal into different frequency subbands. So initially the whatever signal that they are using, they are going to be divided into subbands, and all the subbands are going to be applicable to all n-dimensional signals. Here n stands for number of attributes or dimensions that we are having in our data set. So here number of dimensional signals which is equivalent to number of dimensions in our data set. That means the total data or the signal which we are using for decomposing of the data. Here what we are doing, the signal, or you can say frequency, is going to be divided into subbands, and each and every subband is going to be applied to every dimension in that n dimensional data set. Now, after mapping the subbands to the attributes, here we have to derive, or we have to transform the data. So, data transformed to preserve relative distance between objects at different levels of resolution. That means at every point, or we can say for every each point, we have to find out the distance between objects. Now, to find out the distance, we will see some similarity metrics in later slides. Here, the ultimate objective here, when we are trying to transform the data, here we want to find out the distance between objects at different levels of resolution. If we look at carefully here in this diagram, it is not in a proper condition. That means whatever diagram we are having here, it is not in a visible condition properly. If we look at the output here, we got noise eliminated picture here. It is a commonly used picture for MATLAB applications. So after eliminating noise at various levels by taking the various subbands of the frequency, finally we got this one. But it looks like very simple activity, but to get this final accepted output, here we have to apply more number of distance measures have been applied on the signals or the data at various levels. Now, after performing distance among the objects, we started creating some clusters, and based on the similarity and dissimilarity, we started forming clusters. If any outlier has been identified while forming clusters, those outliers are going to be neglected, and again clustering activity is going to be repeated until we will get the distinguished object. So, and these techniques are used mostly for image compression technique. So, whenever we are using image related applications or image related domains, we can go for wavelet transform as a technique to apply dimensionality reduction. Now, in this, how this wavelet transform will work? So, here we will use discrete wavelet transformation technique, or mathematical models are going to be applied on each and every data. Here, data means here we are, let us take, we are taking a linear signal. Now, to achieve this discrete wavelet transform, or you can say discrete Fourier transformation technique, we can apply all the two techniques together. What is the main objective here? We want to generate a multi-resolution image analysis. Now, what is going to be done in discrete wavelet transform? Here they will apply data compression operations. That means it store only a smaller fraction of the strongest of the wavelet coefficient. That means before retrieving or recreating of the image or compressing of an image, will be started by taking the acceptable portion of the data, and that portion of the data is going to be used for the initial construction, and the process is going to be iteratively applied on the entire data set. Similar to data discrete Fourier transformation technique, we will apply a lossy compression technique while using in image compression technique. Now, to apply wavelet transformation, there are two commonly used techniques there, either by using Hart transform and Debussy signals here. Here we are using two signals. One is a Hart signal, which is look like a binary signal, and Debussy it looks like analog signal. These two are the commonly used signals or frequencies which are going to be used to create or to apply Fourier transform or wavelet transform approaches. So, each transformation will have two functions, smoothing and making the difference between the two signals. So, smoothing will eliminate the noisy, difference will give the comparison between two signals to find out the best one. And now in this approach, what we are going to apply? For every pair of data set, two sets of data is going to be taken, that is average of two sets is going to be taken by taking L by 2. Now these two functions are going to be applied recursively until reaches the desired length. So as we discussed earlier, we are going to start or apply the procedure for a small portion of the data, and that portion of data is going to be applied, or the techniques are going to be applied recursively on the entire data set. Now, how the wavelet decomposition is going to be done? So, to apply wavelet decomposition, we can take the help of any mathematical tool. How it is going to be done here? Look at here. Here we are applying some hierarchical decomposition of functions. Now, what we are doing here, we want to transform the given data. So, here given data set is S equal to the values are 2, 2, 0, 2, 3, 5, 4, 4. So, that is the initial given data, and that data we want to transform into the required output applying wavelet discrete transformation. Now, after applying the transformation, or you can say wavelet technique, the resultant output is in the form of, the converted output is in the form of like this. That means here 4 has been converted to 0, and again the last but one is converted to -1. Now what they have done, they applied some compression approaches. That means many small detail coefficients can be replaced by zeros, and relevant values we can keep it like this. Now here with resolution 8, with resolution value 8, we got the average values of the given data, or you can say given image is like this. Now from this, initially we have not applied any technique, so we won't get any coefficients here. When you go for the second iteration, here resolution was reduced to 4. That means among 8 values, we want to find out the best 4 values here. So here, so from these two, 1 has been taken, 4, 4 and 1 has been taken. That means after applying the decomposition functions on the data, finally we derived 2, 1, 4, 4 as an output. Now among all these, we find out the detailed coefficient values of the given input data set. And again we are applying the recursive approach with the resolution 2. We want to find out only the best 2 average values. So here the average values are 1, 1 by 2 and 4. For this, the coefficient values are 1 by 2 comma 0. And finally the last step, we applied only resolution when we want to find out only the best result, that is 2, 3 by 4 here. Here finally we got -1, 1 by 4. So this is the way of applying recursive nature. Let us say if we started with the resolution of 32, then we have to repeat this process up to 6 times. Let us assume we are having a very large image, which may have a pixel size of 256 by 256. Then we have to apply more number of iterations. If it is a 3-dimensional image, then we have to go for n number of iterations depending upon the target value. If you look at that Haar coefficient value, whatever we derived here, in this Haar wavelet coefficient, we applied the decomposition technique. That is, here we are generating an error tree. That means the plus value indicates positively decomposed, or minus indicates the value has been neglected or not considered during the generation of the output here. So here the coefficient values have been derived starting with the highest value, that is 2.75, and the 2.75 is going to be divided into the required length value, that is L by 2. So here we are applying the length decomposition of that given value here. So initially the total value is 2.75 here, and it was decomposed by applying L by 2. So here we got -1.25, the nearest value. So this portion is going to be eliminated here. That means only this portion is going to be considered. For the reason, so 0.5 is in positive side. Sorry, this one -1.25. After applying, after applying reiterative approach, here we got 0.5 is the next L value in this. So this portion already we completed, so it is not going to be considered. In this remaining portion, one portion has been taken, remaining portion has been eliminated by applying decomposition here. So here we got on the plus side, only small portion is came into the picture. So here we derived like this. So this is the way of going, repeating the process till we get a final value. So every time the length is going to be divided with 2, and the process is going to be repeated every time. So this is the way of constructing an error tree, or you can say hierarchical decomposition of Haar wavelet coefficient format. Now, why we have to go for a wavelet transformation? Why? Because it looks more complex activity. Why we want to go for a wavelet transform or discrete Fourier transform or any other transformation technique? Here, these transformation techniques are made up of with sharp Hart filters. These filters will smooth the data and they'll try to eliminate noisy compared to other techniques more effectively. That means they'll create more emphasized cluster region by eliminating the noise. That is the first one. It will suppress the weaker information which is at the cluster boundary. That means while making grouping of clusters by taking the similarity between the objects, if any value which falls boundary of the cluster, it will be treated as a weaker value and that is going to be eliminated or suppressed. Like this, iteratively we can do two operations either by selection or by suppression of the data, that is weak data. So that is one of the advantages here. To remove the outliers, transform techniques are the best approach to remove the outliers. That is, the insensitiveness of the noise can be identified and can be eliminated, and relevant to the input value, how the noise is going to be eliminated more effectively in this option. And second one, we can go for multi-resolution operations here. That means the arbitrary shaped objects or clusters are going to be formed at different scales and different levels. And when we look into the efficiency, that means how best the algorithm will generate the output, it depends on the complexity of the object, that is O of n, the big O of n. That means number of times the operation is going to be iteratively applied on the data set. And here, and one more limitation in this algorithm, or you can say approach, is for low dimensional data it is best applicable. That means only applicable to low dimensional data. When we are having huge number of dimensions in the data set, these approaches may not produce the better results. And the second technique is the principal component analysis. So till now we have seen wavelet transforms using Haar and Debouche's signal. Now the second approach is principal component analysis. This is one of the oldest and commonly used approach to find out dimensionality reduction. That means the principal component analysis works on the concepts of linearity, identifying the linearity dependence among the attributes. So there are some restrictions here. The principal component analysis will do linear separability on the data. And the next one, how the linear separability is going to be selected, it will be created by applying the required eigenvalues, and eigenvectors are going to be created. And after creating the required eigenvectors, the best eigenvectors are going to be taken based on that dimensions are going to be eliminated. So here, the principal component analysis always to find out a projection among the data set. That means for every attribute, it will try to observe what is the projection values of the attribute. Look at here. Here we are taking, on x-axis we are taking a variable called x1. On other axis we are taking a variable called x2. So between x1 and x2, the attribute values are going to be projected and they will find out how linearly they are relevant to with each other, or in reverse approach, how linearly they are separable to each other. If you look at carefully here there are some values have been found in between x1 and x2, and how can we make linearly separable? That means, so among these points, let us see here we have drawn one line here with some slope. Now this line is used to find out or to apply linearly separable of the attribute. That means, let us assume we are having some 50 attributes. Among 50 attributes, we want to find out the most important attribute and less important attributes. So here we got some more important attributes which are going to be represented in the form of circles, and less important attributes are going to be represented in the form of stars. When we are having all these attributes, how can we separate them? Let us say, if we draw a line, between these O symbols and star symbols, here let us assume we separated effectively. When the attributes themselves, if they fallen on their similar side, it is very easier. Let us take here. Just observe here. When the attributes are like this, how can we draw a line? Because in this example, all O symbol attributes and star symbol attributes are separated together by applying some clustering technique. So it was easier to divide by drawing a line. But if the attributes are like this, if we draw a line like this, on both the sides we are having important and unimportant attributes, then how can we separate and how can we apply the dimensional reduction? So that is a problem in principal component analysis. That means when the attributes are linearly separable with each other, then we can apply principal component. When they are composed with each other, then it is very difficult to eliminate. Now how can we do this? So this is called the non-linearity. They are not separated linearly. Now to apply non-linear data separation, we have to go for alternative techniques. Because in principal component analysis, there is no way to get linearly separable attributes under dimensional reduction. So the alternative techniques are, we can go for autoencoders, which is not in the syllabus. Anyhow, for information, we can learn the names itself. Either by applying autoencoders, we can go for both linear and non-linear separable. That means, so here there is one option. Here we can draw a curve and we can separate them. This is one option. Or on this, there is one more option. On remaining values, we can separate all the values here. So this separation is not possible by drawing a straight line, or you can say linearly. So this is the way of decomposing, applying a principal component analysis. Now what is happening in principal component analysis? Here we are applying some projections. We want to find out a projection that captures the largest amount of variation in data. And second one, original data is projected onto much smaller space, resulting in dimensionality reduction. We found the eigenvectors of the covariance matrix, and these eigenvectors define the new space. So here mathematically we are trying to predict the eigenvectors and eigenvalues. After finding the eigenvectors and eigenvalues from the covariance matrix, we are picking the best value and that relevant attribute we are selecting, and remaining values are attributes we are not considering for the analytical activity. So in this manner we can separate dimensions linearly. It is not possible to apply non-linear dimensionality reduction. Now here we are having some limitations here. For given n vectors from n dimensions, here we are drawing some orthogonal vectors that we have seen in the previous slide. We are trying to draw orthogonal vectors for all the attributes here. So here we are having total n number of dimensions. There are total n capital N data vectors, small n dimensions. Here we want to find out k less than or equal to n. So here k is always equals to n only, less than or equal to n. That means there is a possibility to draw all orthogonal values which are equivalent to the count of dimensions here, and that can be used to represent the data. Now what we are applying here, we are performing the normalization on the input data. Apply normalization input data. Each attribute falls with the same range. Next one, compute orthogonal value for all k values here. That means for every attribute, calculate the orthogonal value, that is principal component. Whatever eigenvectors we are generating, that eigenvector can be treated as a principal component for individual attribute. And next, for each input data vector is a linear combination of k principal component vector. That means here we are comparing all attributes with each other. If they are linearly separable, we can do it. Next, the principal components are sorted in decreasing order, that we can call it as a significance or strength. Since the components are sorted, the size of the data can be reduced by eliminating weak components. That is, those with the low variance using strongest principal component can be considered for analysis. So here we are trying to eliminate the weak components. Now, and one more restriction here, principal component analysis works betterly, or it will produce better results only for numerical data. If you are having any string data, we have to apply data encoding techniques, and then we can go for principal component analysis. And the third variant of applying data reduction is attribute selection or attribute subset selection. So till now we applied reduction, dimensionality reduction. Now what we are doing here, we want to select the appropriate attribute or subset of attributes. So here, redundant attributes. That means if any data is having repeated attributes, eliminate them. Duplicate much or all of the information contained in one or more other attributes. So eliminate the redundant and duplicate values here. Like purchase price of a product and amount of a sales tax paid. If you look at carefully, purchase price of a product and amount of sales tax paid, which are relevant to each other. And next one is irrelevant attributes. The previous case we identified duplicate values. Next here we are looking into what are the irrelevant attributes. Contain no information that is used for data mining task at hand. Contains no information that is used for the data mining task at hand. Example, student ID is often irrelevant to the task predicting student GPA. So here student ID or student roll number is important for a student database, but to find out the GPA of the student, it is irrelevant. Student ID is irrelevant. We are not saying that attribute is irrelevant. That attribute is irrelevant for the task called calculating a GPA, but it requires as a basic information of a student. Here, how can we identify the irrelevance of the attribute? It depends on the task or the activity that we are applying. Next. Now, there is another approach, the heuristic approach. That means, how can we select the feature subset selection? Here, some commonly used techniques they proposed. There are 2 power d possible attribute combinations for d different attributes. That means, let us assume if you are having 2 attributes, then there is a possibility of finding 2 power 4 attribute combinations. Let us say, here we are having employee ID and employee name. Employee ID, employee name on one side, and 2 mining attributes and others like department name and department name. When we are having these attributes, we can have a combination like employee ID and department number, employee ID and department name can be derived, or employee name related to department number, employee name and department name. So these are the possibilities of generating 2 power d combinations of relevant attributes. Now in this approach, we can go for a typical heuristic approaches like find the best single attribute under the attribute independent assumption, choose by significant test. Among all the existing attributes, find the best single attribute. That is one approach. Second one, go for stepwise feature selection. That means among the existing n attributes, find the best first attribute, repeat the process, go for the best second or second best attribute, repeat the process, go for the third best attribute, repeat the process until we reach our target. Let us assume out of 10 attributes, we want to find out best 4 only. Now we have to repeat this process 4 times to find out the top 4 best attributes. So this is called stepwise feature selection. And there is a reverse approach, stepwise attribute elimination. In first technique, we applied stepwise attribute selection. Here we are trying to eliminate stepwise attribute elimination. That means repeatedly eliminate the worst attribute, or you can say unimportant attribute in this option. Or there is another option, we can combine both. Stepwise forward selection or stepwise backward elimination. We can combine both techniques. So this is best combined attribute selection and elimination. And the optimal branch and bound can be used and applied for the selection of the attribute. So these are the attribute selection and approaches are there. Okay. So in this session we have seen dimensionality reduction. In the next session we will see the numerosity reduction under data reduction techniques. Thank you.